Good afternoon, everybody, and welcome. In this defense, the dissertation of Marek Nečada, Master of Science, will be presented for public examination for the degree of Doctor in Science. Dr. Vincenzo Giannini from Institute for Structure of Matter, Madrid, will act as the official opponent. As the official custos appointed by the Aalto School of Science, I declare this defense open.
Thank you. Honored custos, honored opponent, esteemed audience. The title of my dissertation is D-matrix modeling of plasmonic nanoparticle arrays. If there's someone in the audience who finds this a little bit too cryptic, we have now also online audience, then don't worry, I will try to decode it for you. So first of all, let's make this work. And let's talk about plasmonic nanoparticles. So by plasmonic, we mean basically metallic nanoparticle. Plasmons here refer to the electron plasma oscillation in metals. The plasmonic nanoparticles have many interesting properties. One of them being that if we illuminate a nanoparticle with light, here, when we talk about nanoparticles, I should say that we are talking about diameters of around dozens of nanometers. Then it has the property that it enhances the intensity of electromagnetic field in the very vicinity of that nanoparticle. And this can be used, for example, to facilitate coupling between external radiation and basically any substance that can be in the vicinity of the nanoparticles, such as fluorescent dyes. Then if we put those nanoparticles in periodic structures like here, then they have some interesting properties as well. So there are strong resonances along the diffracted order of the lattices, depending on the geometry that the lattice uses, and these are quite fascinating and have found use in fundamental research. Fascinating physics has been observed there, like lacing, distributed feedback lacing, Bose-Einstein condensation of plasmon polaritons, and they have also potential in various applications such as sensing, solar cells, or for example photography. There has been this meta lens concept recently that can be used to enhance lenses. Okay, so the problem is that when we want to if we want to develop new nanoparticle arrays, or if we want to study, to understand the phenomena that we see in the experiments, we need to have some effective method for modeling the optical response of the nanoparticle arrays. But for larger arrays, this can be quite challenging. Let me demonstrate it on one approach that is quite relatively popular, the boundary element method. It's a frequency domain method, so we assume that everything oscillates at a certain frequency and it oscillates harmonically. So boundary element method uses triangular meshes to model the boundaries between different optical media. In this case, it can be, for example, metal inside the mesh. That is the metallic nanoparticle, and around there can be air, or it can be some substrate or whatever. And then the method uses the surface currents in those triangular elements as their method of description, and those are basically the degrees of freedom of the model. So if we have here a particle that can have several, well, hundreds of elements, then there are some few hundreds of discretized currents inside. Then, well, how this works basically is that if we illuminate it with some light, then the light incident on the surface will excite some surface currents. Those surface currents will then radiate because if you have a current that is changing in time, we have harmonic currents here, it will radiate. And it can then induce currents in the other elements as well. So we have interactions between all those triangular elements here, and we will have a matrix that describes this interaction. So in the end, to solve how this nanoparticle, for example, responds to external radiation, we have a linear equation where on the right-hand side we have the incident light encoded into some initial surface current. Then we have the matrix that describes the interaction, and then we have the unknown currents. Once we solve this, then we can, for example, easily calculate the electric fields or scattering cross sections or whatever quantities we need. And here, if we have only a few hundreds of elements, it's just, well, the matrix M here will have few megabytes in the memory of a computer, and it can be factorized and solved almost instantly. But if we have many of those particles arranged in an array, then the problem is that these numbers start to grow quite quickly. So if we have 10 times 10 array, and we use this method in the same manner, then we will have 100 times larger the surface current vector, and we will have 10,000 times larger the interaction matrix. So this means that basically from few megabytes, we are suddenly up to several dozens of gigabytes of memory that we need to solve this. And it will, even if we had the memory, then it will take time to compute. And this is basically, we cannot go much further. If we wanted to simulate 100 times 100 array, well, that is a no-go because we simply won't have the memory. So what can we do to simulate larger arrays? Well, one of the possibility is to just approximate each nanoparticle just as a dipole. So basically, then instead of we will have just three unknowns for each nanoparticles that will be basically the dipole oscillations in three possible directions. We will have some polarizability tensor 3x3 matrix for each nanoparticle. We have some Green's functions between them that will facilitate the interactions between them. And this way, we can, with my laptop, I can simulate systems with thousands of nanoparticles, which if they are simplified to dipole. The problem of dipoles is that, well, it's too rough. It's too rough approximation, and very often we have, for example, seen an interesting placing modes. I will show that later. That included quadruple excitations in the in the nanoparticles, and the dipoles in that particular mode were negligible basically. So with this dipole approximation, we would be unable to simulate them. So what can we do? We can add more multiples, and this is basically the idea behind the T-matrix method that my thesis focuses on. So how is it done? Well, there is a concept of vector spherical wave functions that can be used to expand any kind of electric field, electromagnetic field around a nanoparticle. It's a basis, well, this is the definition, but it's not important. The important thing is that we can expand basically any field like this. And then for each of like incoming exciting members of this basis, so for each incoming spherical wave, we can calculate the scattered fields with basically any method. And we will get this again in terms of spherical vector waves. So there will be, and those will basically, by doing this, we get coefficients of expansion of the spherical vector waves of the scattered fields. And this basically gives us a column of the so-called T-matrix, which uniquely describes the scattering properties of any linear scatterer. So then if we have an expansion of incoming field, we'll just throw it here, like it's the A on the right-hand side. We'll throw it into the T-matrix, and we will get coefficients for the scattered fields. So if we have more particles, then we can do this for each nanoparticle, this procedure, and then we can re-expand the scattered fields from one particle in another origin where another particle sits, and that will be exciting field for that another particle. And in the end, we will again, those re-expansions are ruled by so-called translation operators. Those are super ugly expressions, but they can be calculated. Then basically using this, we can again get a linear system, which in simplified like block matrix form looks like this. A similar system as to what we have in the BEM method. But now the vector here is much smaller than in the BEM. So for example, if we were include all electric and magnetic dipoles and quadrupoles, then that means like 16 numbers per particle, like 16 degrees of freedom. And well, although it's like more than in the dipole approximation, so we will have to have like smaller system. So instead of thousands, we can go like to several hundreds. But it's still a very large progress compared to the boundary element method, for example. But actually, we can do one thing to enlarge the size of the array we can simulate a lot, because most of the structures we are interested in have spatial symmetries. And if we have spatial symmetries, we can use group theory to actually decompose this linear problem. The matrix on the left-hand side is 1 mean minus TS, can be block diagonalized using group theory, and each of the blocks can be solved separately. And this means that, for example, if we have a rectangular lattice with rectangular symmetry plus horizontal mirror symmetry, then we can get this group will have like 8 irreducible representations, so we can decompose it in 8 smaller matrices with 2 degrees of freedom. Each will have around 2 degrees of freedom per nanoparticle, And that is actually better than the dipole-dipole approximation that will have 3 degrees of freedom per nanoparticle. So with this, we can actually simulate full-sized arrays that we have in our experiments up to, for example, quadruple order, which is quite a big advance. You cannot do this like with the BEM. It's no go with the dipole approximation. Well, you don't have the quadruples there. So this is actually one of the things that I developed in my my dissertation. Another one is that I studied how this method can be extended to infinite periodic systems. So of course in reality we have finite arrays, but it's useful to have this method also for infinite system, because then we can calculate the band structure, the photonic band structure of those arrays, and we can, for example, determine what effects that we see are due to the bulk phenomena and which belong to the finite size effects. So yeah, basically this work I have, this theoretical work on the method has been implemented in what I call the QPMS photonic multiple scattering suite. It has core C library and some Python bindings. It's published as a free software under the GNU GPL license, and this is where you can access it. So you're very welcome to use it, and for example also to improve it and develop it more. So now I will go in the time I have left to some applications of these methods for real-world experiments. So for example, here we had an observation in a square array of silver nanoparticles in some active fluorescent medium. We have observed lasing, and we have observed lasing on actually 2 frequencies. One was in the normal direction from the array, and the other one had a small angular deviation. So our hypothesis there was that actually one of the lasing modes is a so-called dark mode that is quadrupolar in essence. So basically the nanoparticles have quadrupolar electric excitations, and this would actually not radiate outside in case in the infinite lattice limit. So therefore, dark mode name. So and basically, with my method, like this T-matrix method was used here to back up that hypothesis that this is actually the dark mode with the quadrupolar excitations. So then a similar thing was done here in well, not completely similar. In this experiment we had again like rectangular array, this time with nickel ferromagnetic nanoparticles that are interesting, that they can be influenced, their optical properties can be influenced by magnetic field. And here basically there were again several lasing modes, and here we did some mode analysis in order to see what modes are actually lasing and how it works. And another lasing experiment, this time for hexagonal lattice, was done here. Interesting thing, this was not like a gamma point lasing in the normal direction. It was a K-point lasing, which is like a different part of the Brillouin zone. And here we again did some analysis. Here we did some group theoretical analysis of the observed real space and also K-space images in order to determine like what are the polarizations in the system and to which irreducible representations to which one of the possible modes it can belong. So which one is actually lazy. So yes, this would be for the introduction here. I thank you for your attention, and now I call upon you, honored Dr. Vincenzo Giannini, appointed as the opponent by Aalto University School of Science, to present the observation that you consider appropriate for this dissertation.
Thank you, Marek. Can you hear me anyway?
Yes, I can hear you. We can make... Yes, we will put you on the screen.
It's okay for me. I mean, yeah, up to you.
Yes, and we can hear you, although it could be...
Maybe it's better your thesis than myself, but up to you. I mean,
can we make it louder? Okay.
Okay.
So can you speak for a minute?
Yes.
For a second. So we need, how loud are you?
Is it okay?
Is it okay?
First of all, I would like to thanks for...
The audience here says that it is okay.
So, okay. Should I start?
Please.
Okay, thank you, first of all, to give me this possibility to learn something with your thesis. So, really nice presentation. Let me review a bit what has been your contribution to the field. So, your work, Marek works is focused on development on a really powerful tool for the used for the scattering of light in kind of general arbitrary shape, if you want, nanoparticles or particles in general. And it's a kind of a very well-known method. It's old and very powerful, but there aren't so many, let's say, code out there extension that make able to, let's say, that are useful to the community. So in that sense, Marek did a really great work. This method is quite fast. It's computational. Uses low memory, as we saw, and I would say it's a kind of complicated to implement it. It's not hard to understand, but it's kind of delicate to do it properly, because also it's quite simple to have some mistake. And I saw that you did a really good job in that direction. You back up your result, works very well. He extended that method to infinite array, let's say, using an Ewald approach. That is a good idea, because in experiment, usually you have to consider, let's say, infinite system or almost infinite system. And this is a big problem of the other usually technique used in electromagnetism as the bundle element method, FDDT or similars. And in that direction, let's call it the transfer matrix is a really good option. Something else that I really appreciated in your work was the extension to that method to quantum system. So I saw that you started to have a look to what will happen if we quantize the electromagnetic field. You didn't look to the quantization of the, let's say, of the electronic part, but that makes completely sense. It became much stronger, bigger problem. But you started with a macroscopic quantization. So a quantization, let's say, a optic, quantum optic. That is a really great way to start. And as well as you showed, you checked this method I mean, you had a look when if you can forecast lensing, or you can explain lensing from arrays where you have a gain media, and successfully, I have to say. And so definitely you did a really great job. And in particular, I am impressed about 2 points of your work. One is the extension, as you tell, the initial extension to the quantum case. That is a good idea, and this will be really useful to the community. And the second one is the effort to make your code open. That's something that we as scientists we should consider. Actually, I think it's our obligation to the society. And you did very well putting your code in GPL license, so I really like it. With that, now this was the overview of the fast overview of what you did, and I also have some question on your more detailed question on your work, if I can ask now, right?
Yes, please.
Should I start with the question? Okay. Well, let's start with something that is to break the ice, so something simple and nice. What is the most, let's say, the result that you are most proud of in your work during the thesis, and why?
Okay, well, probably what I'm most proud of is like the implementation of the method, because it's really like something that it's, that there are some implementations from the earlier times that are that are available there, but they are not very extensible. And so basically, if I now started to thinking about on what I spend the most effort in my work, was actually coding in the end. So, and debugging and stuff like this. So it's probably like this thing that I'm proud of, that now we can, if you have a problem, if you have some nanoparticle arrays, you see some results, I can get you the results relatively quickly with my code. So, and it's quite variable. If you tell me now that, okay, we use nanoparticles that have some special shape, it can be plugged into the code quite easily. So, okay. Yeah, so this would be the thing.
Yeah, I suppose. I really see what is your what are your aims in research. So yeah, I like it, I have to say. Okay, now speaking about the method, this is a good. So we go a bit more in detail. Did you check how it compares with other methods? I saw with the BEM, for example.
Yes, I did it with boundary element method because yes, I wanted to compare it, like benchmark it with some, in the first place, with some integral method, some frequency domain integral method that would be near to it. There was one problem that I encountered that was actually a quite annoying bug in the boundary element method code I used. So the benchmarking then concluded in actually having to debug that other code for the boundary element method. So then what can you benchmark it with? You can, yeah, well, you cannot benchmark like multiple scattering with the let's say solution for a wave. You can actually benchmark your like T matrix computation procedure with this thing, with the solution. But yes, it's so I benchmarked it with this boundary element method, and then after finding the bugs and so on, there was some kind of good agreement in the end. So
okay.
There it would be also possible to benchmark it with some differential method, for example, FDTD. I was considering it. I didn't have the time to do it properly in the end. But yes, so some benchmarking.
Can you speculate a bit on the time? Let's say, I'm pretty sure that if you have a single nanoparticle, the transfer matrix will be much faster than except the sphere, well, much faster than boundary element method, for example, FDT or whatever.
Yeah.
But what about a cube? And I will tell you, or maybe you will understand why I'm asking a cube. Do you think it could be faster, or an array of cubes? Nanoparticle.
Yes, well, with array of cubes, what I would do is that I would calculate the T matrix of a cube with the, for example, boundary element method, and I would plug it into this multiple scattering code. Now, with a cube, there is, of course, the question, where should we do the truncation of the multiples?
Exactly.
So that would depend on the size of the nanoparticle, and the problem is that it has sharp edges, right? So, but
do you see where is the problem? Where could be the problem? I mean,
yes, I see where could be a problem. The problem could be if they were like in close vicinity to each other, or you would study some, for example, some fields in the vicinity of the cubes, then it's very possible that there would be really many terms, many elements of the T matrix that would be non-negligible. So you would, in the end, still have quite a lot of degrees of freedom there. But if the cubes, if you have only an array of cubes and those are sufficiently far away from each other, you can actually use this method quite well, because the higher multiples that will appear there because of the because of the edges, their like radiation patterns or this vector spherical wave that is associated to those higher multiples, their intensity drops quite rapidly with the distance from the like origin from the source. So if the next particle is far enough from the source, then it doesn't feel too much of it. There is, an important note here is that all the spherical vector waves asymptotically have like similar asymptotic radial asymptotic behavior far from the origin, when it's basically some exponential like oscillating term divided by distance. But the thing is that with those edges in the cubes, for example, it's really that the term itself, maybe it will be quite small also in the T matrix, depending on what normalization do you use. So it will appear small, but if you don't have anything really like close to that nanoparticle, then compared to the other wave contribution, those will be really small that you probably won't even notice in the system anyhow.
Yeah, probably you're right. Except in the situation when you really need a lot of component in your expansion to map your single particle, let's say.
Yeah, it's really heavily depends on the distance, and of course, if you have like small distances between the particles, then you will have. I showed the equation which included the T matrices and the translation operators. If the distance is small, that even if you have like small elements in the T matrix, you have diverging elements in the translation matrix. So that's a potential problem. So that is something that has to be checked if you know that you have either large particles or small distances between them.
Can you think in a possible solution? It's not a simple solution, but can you think in a solution of this problem?
Well, So one of the solution is to simply include more terms in the T matrix, and the other solution would be like to consider bigger aggregates, like, well, at the microscopic level, or on the level of like
more mathematical level. Let's say, do you think could be helpful to change the basis instead of spherical waves, something else?
Sorry, I didn't hear it.
And will be useful to think in a different basis.
Yes, different basis than spherical basis.
Yeah.
Well, there are people using Cartesian basis for multiple scattering as well. The problem with the so-called like Cartesian, how is it called? All those Cartesian waves, Cartesian multiples, is so okay. If you have the cubic particles, it makes completely sense. Like, or no, I would say okay. It's like better suited with respect because you have simpler way to describe the cubic particles in Cartesian coordinates than you have, for example, spherical particles. So yes, you could use a different basis. You could use the Cartesian basis. People have been doing that. I prefer to avoid it if possible, because like the spherical base has some like really nice properties compared to the Cartesian multiples. For example, with the Cartesian multiples, you get stuff like what is called anapole, and that is basically like a thing that, yeah, it basically means that you see your like some dipole contribution vanish, but it's more of like a mathematical thing there, that it's simply some artifact due to the choice of the coordinate of the basis. If you use the spherical coordinates, they have many nice properties. So first of all, you have this like rotational invariance. You can change. You can rotate the particles by just basically linearly modifying the T matrix, and you will get with this linear transformation, unitary transformation of the T matrix, you will get a T matrix for a rotated particle. If you wanted to rotate your T matrix in the Cartesian basis with some weird angle, well, it would be probably not easy with the Cartesian Cartesian basis.
As you're saying it, that practically one of the good point of a spherical base is the fact that if you're interested in scattering from a different direction, or you have unpolarized light or whatever, this method should allow you a fast computational approach, right?
Yes.
Did you ever use it? I mean, this is one of the most used property of this code for people that works in scattering by many particles and atmospherical particle, for example, because you would like to know what's happening when you want to average on angularly, let's say. Mm-hmm. Did you use any of this property?
I didn't need this because this is used very often. If you have, for example, if you assume some random behavior in your system, and as we have used it for like nicely structured periodic systems, then I didn't actually have to use it in my applications.
Okay. Yeah, there was just a curiosity. Okay, speaking about the periodic system arrays, So you compared what you get when you just sum the contribution, and when you use, for example, an Ewald approach, or when you use some group theory approach. Okay, so clearly you tell, okay, you can make much faster if you know the symmetries of the system and these kind of things. In that direction, do you think it's possible to do something more? Do you have an idea if it's possible to improve a periodical array of scatterers?
Well, improve in which sense?
Do something a bit more faster than what you get with, well, a lot more faster actually, than what you get with using the group theory approach.
Well, the group theory approach doesn't make it for like the periodic arrays too much faster. It's just like, because you have only like small number of particles in a unit cell usually. So the group theory doesn't give you here like so much edge in the sense of speed or computational complexity. What in the infinite systems, what the group theory is useful for is analysis of the modes. So you can analyze which modes belongs to which irreducible representation, and that will help you if you want to calculate, for example, the photonic bands of the system.
Yeah, but you, for example, comment that you can reduce in blocks your matrix, and you even were saying that it became faster than to consider a double approximation, for example.
Yes.
Okay, so what, you have a good improvement that direction. Well, for example, compared to a bundle element method, I mean, there's no way that you can do a so much big structure. What I was thinking actually is, do you see any possibility to make it real, to solve your problem periodically? To say, I have a particle or two or whatever, I have a unit cell, and fix periodical boundary condition. Do you see a way? Do you think it's possible to do with transfer metrics? Is any? Do you never stop to think on it? I don't know if you have any consideration. So I'm saying really imposing boundary conditions that are periodic. So you work on a single particle. Let's say. Do you think it's possible
to improve?
Yeah, to do it
with transfer matrix.
Exactly. It's a tough question. Don't worry. I mean, it's just let's say, give him your vision, your point of view.
Yeah. Well, I didn't like think in this direction too much, because I mean the speed up I had like achieved with this D matrix was already like with this eval summation, although the summation takes time as well. So I didn't like see too much reason like to improve, like go for the constant.
So you're saying it's already very fast with Ewald practically.
Yeah, like I mean, if you were, for example, to calculate when I did, for example, some images with like transmission properties of the array. So there it was. I was already like scanning over many frequencies. So and then if you have the the lattice sum method, you have to you have to compute it again for each wave vector separately as well. So then it starts to accumulate, the amount of time that it's required for computations. But for example, well, yeah, otherwise it was already like satisfactory fast that
Okay, now makes sense. I mean, I was just checking if yeah, because probably an extension that I don't know, I never saw out there is to impose periodical boundary conditions some way, really an infinite system. That would be curious to see if it's possible, but okay. You are right here. You say it's enough fast, so why complain? About when you started your thesis, it was curious that you start, and well, you did well, starting the most general case. Yeah, you started with Maxwell equation in a very general case. I understand that probably you were not interested on the topic, but what about? Do you think that it's possible to extend this method to case, for example, to magnetic materials? Materials that where you have a surface charge, surface current, so these kind of things, or anisotropic material.
Okay, so I'll start with the anisotropic materials. I'll start from backwards because I will get to the rest then. So with anisotropic materials, it's fine if you have anisotropic material inside the particles, because then it still has like the T matrix and so on. But then you have the assumption that that the background medium is anisotropic. If it were that is isotropic, sorry. If it were anisotropic, then you wouldn't have this natural spherical vector wave basis. You would have to use something else. In principle, it's possible. The thing is that the spherical vector wave functions are like still like relatively nice analytical functions. And for example, I have like tried to only briefly like get some overview of this topic. But as far as I know, that if you have like the anisotropic materials, then you cannot, for example, get an analytical expression even for the like basic Green's dyadic. So and this.
I mean, you mean the background? You mean all?
Yes.
Yeah. Okay. Yeah. No, but you are right. But that case, let's say, is a kind of extremely weird case.
You had some basis, like if it were possible to, do it, perhaps not analytically, but in some like efficient, that if you were in some efficient way able to get some basis like this, then why not? But I think it would be challenging to find that good basis for that.
But I mean, I agree with you that the real physical problem that people get interested on is the one where you have particles that are anisotropic, not the background.
Okay. When particles are anisotropic, then it's not a problem for the method because, well, you somehow need to calculate the T matrix for the anisotropic particle, but once you have it, you just use the same formalism for the rest. And you can actually calculate this properties, this T matrix for the anisotropic particles. You cannot do it, for example, with the boundary element method, but you can use it with some volume formulation. It's possible.
Okay. What about the magnetic field?
Magnetic field, yes. This is like similar. You can okay. So you can have some ferromagnetic particles. That was actually somehow background of that research or motivation of that publication. Was it for that we had this lacing in the arrays of nickel nanoparticles. Those are ferromagnetic nanoparticles which have some potential, like, well, there are magneto-optic effects in those if you put the particles in magnetic fields, it will lead to magneto-optic Kerr effect. So you can if you are able, again, to calculate the T matrix for the magnetized particle, then you can again get the modified scattering properties of the particle in a magnetic field. And I actually, at some point, I did some simple model for a spherical particle that would have this like magneto-optic properties, and I have had a look a bit on how it would it affect the T matrix. So yeah.
So there are chances, I mean, to extend it.
I think it's possible, yes.
Okay.
Well, there is still this like assumption that your system is linear, like in the sense that it linearly responds to the field you send into it. Yeah. Then would there be some nonlinear effects out of this? Yeah, maybe, I don't know. Like,
no, it will be still linear, don't worry about that. Yeah. Speaking about that, we came back to the last point, that was the nonlinear part. Do you see any future possibility for the nonlinear material?
T matrix method, right?
Yeah, of course.
Yeah, it would be interesting to see. I'm not saying like it's completely impossible. So you could basically do some kind of like perturbation theory, like
yeah, that's a good idea actually.
Like approach to get the nonlinear effects in there, but yeah, I don't see any straightforward way forward with that.
Yeah, it's good. This is I just asked it practically because as you worked also with lessing,
yeah.
So maybe you had that thing. I mean, you had you.
Yeah, that would be of course great to have like nonlinearities in there. But, actually, we just see in practice that okay, so the lasing somehow happens on top of those linear modes. It doesn't. It, for example, switches between the modes depending on the pumping intensity and so on. But usually it doesn't, for example, shift. Well, it can do it, but in like normal conditions,
in safe conditions, yeah,
modes in a really heavy way.
Okay, so in that situation, let's say that you have an array of metal nanoparticles and you're interested in lessing. That means that you have a gain media. So the background, let's say, of this nanoparticle will be a gain media. How you consider it in your calculation?
Okay, yes. So one thing is that the there is the assumption that your background medium gives you gain, right, in the system. So like in the linear regime, what you can do is that you include this gain into the basically refractive index of your background material. Yeah. Otherwise,
did you try?
Yes.
And
or actually, well, to be more precise, what I did was that I tried to find. It's actually also in the thesis. I tried to find resonances of finite arrays with lossy and also non-lossy particles. And well, if you have a finite array, you will always have the radiative losses there. So basically, in order to have a mode, a resonance there, you need to somehow compensate the losses, and they are somehow the radiative losses, and they are mathematically compensated by the imaginary part of the refractive index of the background medium. So when you are doing this, for example, with the Bayes algorithm, then you will actually get some complex frequencies there, and those translate in that could similarly be interpreted as complex terms in the background medium.
But in that situation, your background was a real background. I mean, everywhere.
Yes,
with the
but once you get to the
exactly, that was the question.
Imaginary frequency, then it's no longer real background.
Okay. Yeah, otherwise, I imagine that numerically that you will have a weird situation. Okay. So speaking about lacing mode or mode of a system. So you are saying, okay, if I have a finite system, I have my resonance that they have a frequency that is complex. Okay. And you were thinking in the case of a background that is it was again media. But what's about when you don't have when you have an array, let's say a finite array of nanoparticle in the free space? The resonance of that object will be real or complex? What do you think?
If infinite, sorry,
finite.
Infinite, the resonance would be, and without gain or with gain. Without gain, it will be complex.
Complex, yeah, and it will not change the problem actually if you have a background that's actually when you have a background.
If you add into that background the gain, then you will find perhaps some real frequencies there.
Exactly. So practically the idea of the background, as you're saying, is bring down the frequency to the real axis, and so you can have a lacing. So to have a proper resonance.
Yeah, like if in infinite array, basically you have modes that will like never radiate out from the array, as they would in the case of finite array. In finite, you cannot just trap light into a finite volume of some real materials.
No way.
So yes. So it will be always complex unless you have gain or something.
And which method did you use? So I saw, but I didn't know it actually in your thesis. So how you get the complex frequencies? I mean, of a mode.
Sorry, how do I get them?
Yeah, I mean, I remember there was one of the graphs in your thesis was showing if I remember well.
So basically, in order to find the complex frequencies, I use a so-called nonlinear eigensolver.
Mm-hmm.
In this case, it's the Bayes solver, but nowadays there are more advanced solver of that. I have found that just afterwards, after this one was already implemented. That would be maybe more faster and reliable. But basically, if you have a system that is basically you have a matrix equation, and if the matrix somehow is a function here of frequency, if it's an analytical function of frequency, then there are those eigensolvers that can solve this problem for you, well, relatively easy by computing the values of the matrix only around some 1D contour inside the complex plane. So you do not have to, for example, scan over like the 2D complex plane. You just do it along that curve in which you expect the solutions, the resonances, and basically this algorithm will give you the solution for that.
Okay. I have to try one of them. I didn't try. About lacing again, you said that you contributed to, let's say, to highlight or the origin of one of the lacing mode in one of the papers that you published, and that was a dark mode, if I remember well.
Yes.
About that, and you also said something about dark modes. So, what is your definition of dark mode?
My definition of dark mode would be that it's a mode that like doesn't radiate outside the array in the limit of an infinite array.
And one of these modes that you found, do you think will lace? I mean,
Sorry?
a dark mode can lace is the question.
Yeah, it can lace. Like the thing is that like it's not perfectly dark when it's finite. So there is coupling to the pump and everything, and so and it couples out that you can see it. So it's no problem. It actually laces better than the bright mode.
Yes, but I had the impression that when you were speaking about okay, so you said no. Okay, there are two ways to define a dark mode. Let's say maybe one choose what that are not the same actually, and one choose a bit what he prefer, she prefer. That one is that it's a mode that is not radiating, and this is what you said now. Another one is that is a mode that has a zero dipolar moment. Now, I had the impression that from your introduction, also what you said in the paper, you were considering calling more a non-dipolar mode and dark mode something that was not dipolar. Is that right? Or
sorry, I misheard the last sequence. So could you repeat it?
Okay, yeah, don't worry. Some people think, it's a definition at the end of the day, called dark modes something that has zero dipolar moment.
Zero dipolar.
Zero.
Zero dipolar. Okay, zero. Okay.
And so a quadrupolar mode, for example. And I had the impression that in your work it was the same definition, actually. So a quadrupolar mode is a dark mode. Am I right, or
yes, it's dark mode. Actually, you can. There's a possibility, like to approach this, like from the group theory perspective. Now there are. There are so-called the groups have so-called character tables. And one way to determine whether the mode is dark or not seems to be that it has like certain sign in certain symmetry transformations in those characters or character tables of that irreducible representation that is associated with that mode. Yes, and basically it's then equivalent to this dipole.
I'm not completely that is equivalent, but okay. For example, let's take a single particle. Can you have a dark mode in a single particle, a sphere, single sphere?
No.
No?
Of course not. You cannot have...
Let's say two spheres. Can you have a dark mode?
No. You have, like, we are speaking about dark modes in case of infinite arrays.
But actually, okay, if that's your definition, yes. But there are also, let's say, a very well accepted definition that is, if you say that a dark mode is an object with zero dipolar moment, you can speak it also. You can have it also.
Yeah, if you define it like that, also for finite system, that if it's your definition that you can have like dark mode in a single particle as well, but then like,
well, yes,
I don't see then the meaning of doing that, because it will radiate.
There is a reason to do that. That's not a great reason. Is let's think, for example, a two particle, and if you think that are small enough, and each of them you are close to the dipolar resonance, what you can have is a system where you can have a symmetric and asymmetric combination of that. Now, the unsymmetric will have zero dipolar moment overall.
Yes.
And zero emission. So in that case, you have a real dark mode.
Yes. Okay. Yes, I can then see the point of doing that in a system like that. And well, actually, we did that also we did have a finite array in our case, right? And we still call it like dark mode.
Yeah, exactly. This is what I was surprised in part about your array.
But like the idea behind that was that like it's really dark, like in the infinite array limit. So.
Okay. No, sorry, I was just. You are right. Okay. Also, I had some question because it was quite interesting. The work that you are starting to extend it to the quantum regime. That is a really great thing, I have to say, really great thing. You were careful in your thesis to say, okay, when I say quantum, I speak about macroscopic. I mean, I will start from quantization of macroscopic field. So, can you explain why? Is a real quantization? Let me make some kind of last question in that direction. Why you specified it? Where you were so careful to say, okay, this works well, it's good.
Yes. Well, because that's actually that if you start with this macroscopic concept of electrodynamics, you are like from the beginning you are completely forgetting about the electronic structure of matter. So it's obvious that you lose something with that. You lose very important information. You don't have like electron tunneling if you do macroscopic quantum electrodynamics. So like the phenomena you can get from this model are limited to those that are like more related to the photonic part of the whole thing. But like the electronic part is taken, it's just somewhere in the macroscopic definition. So you don't have the microscopic effects there.
Yeah, but I mean, it's not a bad idea. There is a huge big field that's called quantum optics that work just with that.
Yes.
So I mean, it's not let's say a minor thing. I mean, if you can extend it, it's actually super powerful. Now, my question was there. Do you know when is useful your approach?
I think the most known thing that is actually capable of explaining is, for example, the Casimir polar phenomena and stuff like this. So, like these vacuum forces between bodies that are like obtained from this like vacuum in the quantum electrodynamic description that starts basically from the macroscopic formulation. And then what it can be also useful for is that if you have some quantum emitters, you are interested in interactions between quantum emitters, and you want to have some like formalism to couple them to each other and so on. So this is basically what you can use it for.
Let me say this in a different way. Obviously, we expect that in some limit you will obtain the same solution that you get with the non-quantum one, the non-quantum approach, right?
Mm-hmm.
Okay, what are in which situation you get the same? I mean, one, your quantum approach will give you the same result of the classical approach.
Well, usually if you have like low number of photons there.
Yeah. So basically, you have a really great system when you want to work with few photons. That is not a minor thing. So well done, very well done. Yeah. And you cited that okay, this is a quantization of practically just quantizing the electromagnetic field now there. And you say this is usable for Casimir. Does mean this that you will be able, for example, let's say you have your array of nanoparticles, and you want to know the Casimir force that you will get for a test particle that you have on top. Can you calculate it? Can your model calculate it?
I think that yes, but I haven't ever done that. But my expectations is that it would be possible. Yes.
Okay. Can you just review a bit how you introduce the quantum? Let's say why is useful the transfer matrix in order to get this quantum approach?
Okay, so yes, this will require a bit thinking here.
All your time.
Yeah. So one of the possibilities, like why this could be like useful potentially, it would be actually if you had some like many photons interacting when the quantum effects are there. So if you had, so I think that it's my like speculation now, right? It's
Speculate. Go.
Hypothesis that like this T matrix approach would make some calculations maybe easier to do, like exactly in this kind of multiple scattering setup. So, for example, if you were to, yeah, exactly, if you were to study the effects of like Casimir forces or whatever in this kind of nanoparticle array setup, then I think this would be a really, for me this would be the natural approach to take, because I have seen how the, like in the classical case, how it makes the calculations simpler. So I believe that if this is done properly, also in the quantum case, you could get some class of problems, let's say, that would be solved with this approach much more easily than with other approaches. But as I have said, like, this is speculation. I like in the thesis there is like I have somehow formulated some kind of outlook. I have cited some articles. I actually like tried to make this proper quantum electrodynamic formulation based on some article I read, and I tried to rewrite it in terms of the T matrix formulation, but I like didn't have the time to.
Yeah, I saw that you started. Don't worry about that. It's a great. As I told you when I started, I think it's a great thing that you did. Anyway, I mean, even has to be developed more. I agree with you, but it's a good start, really good start. And you also commented on some non-local effect. I don't know. Well, I don't know if you know. Do you know any? Let's say, to proper quantize the matter is tough, and I don't see a simple way. And it doesn't make any sense to ask you, do you see a possibility? Because I mean,
For the non-local effects, like.
But let's stop us to the non-local effects. Do you think there is a way to introduce in your system, in your approach?
So you mean like quantum non-locality, or?
Well, I mean, yeah.
Or
yeah, due to quantum non-local effect, due to small quantum effect, let's say. I mean, you know, if your particle is not enough small, let's say 5 nanometer, you start to have deviation from the classical case, and you can consider it in a simple way if you want, without do a proper, without to write down Schrödinger equation from n electron solve it. I mean, there are ways. I don't know if you're aware about any method that you could use.
Like this is that people do some like density function theory and stuff like this.
That's enough, I think,
but yes, I'm like not very well aware of this kind of this area. So
no, but okay, makes sense. I just was curious as you wrote down about non-locality. No, there are ways that you can just use that you can imagine. You can just think in the quantum effect as a perturbation if you want your system, and so you can write down effects that are due to just the surface. They decay very easily, fast, and you can just correct if you want your system. If you want. There are ways that allow you to write down, instead to solve a spherical particle, let's say, for example, you solve a particle that is spherical with a thin layer of another material that can mimic small quantum perturbation. And I think that with your method it will be pretty easy to introduce it.
So you mean that there would be like the like quantum effect from like gotten from this perturbation theory, and then it would be plugged in my method. Yeah, that I can imagine.
Yeah, there are. I don't know. There is sometimes ago. There was. I don't remember. Maybe 4 or 5 years ago, maybe more. There was a Nature. I think was quite famous because of from the Bamberg group. I don't know if you know it. And where they were studying the tunneling in that case. So there are a lot of work from Bamberg, Eichspurua, Nordlander, this kind of people. I don't know if in where they were able to see tunneling between two small spheres. And they also had a model they call the quantum corrected model or something like that. And the basic idea is, okay, let's incubate the small quantum effects inside, let's say, the dielectric constant, if you want. So there are techniques that I think you could easily to use in your model. And the same is for the non-locality. Non-locality, there are techniques that allow you to redesign your model. Yeah, I mean, you say to incubate your effect in the epsilon. That's what you use. And so at the end of the day, you will do a classical calculation with and I think I mean, if you have time to have a look, that will be a nice add to your.
Well, there is of course the concern about, like, again, like many of those effects are there when, for example, the particles are close to each other. Then you would have maybe some, like, that would be problematic from the T matrix.
Yeah, you're right. I forgot that.
And this is a truncation. So you would introduce like another problems with that.
Yeah.
Yeah.
And speaking in that direction, you don't see any. I mean, let's say, could you think in a code? Because I see that you are pretty good to coding. Can you see a code and a method, if you want, that allow you to jump? So can you define? I imagine that if you have a situation of very close nanoparticle, two nanoparticles that are almost touching,
yes,
maybe this is one of these cases where the spherical harmonics don't do a good job, and it's good to shift to another base. Could you think in a system where, when you are in this situation, just automatically shift to another base, and which base maybe that cannot be the Cartesian, but do you think can we improve this problem of the transfer matrix?
So you mean, for example, if we have particles that are like overlapping?
Not overlapping, it's very small gaps.
Very small. Okay. I mean,
so I'm thinking, can you do a kind of asymptotic expansion around the gap that but that is not made with the spherical harmonics, maybe, and you patch with the spherical harmonics or something? I'm saying this.
You can basically always do like some switch between spherical harmonics and different bases. You will have well, it's just a matter of finding the coefficients between those different bases, the transformation. So like in principle, why not? Actually, when we do the boundary element method to calculate the T matrix, in essence, we are also doing like some switch between the basis that is used for the surface currents in the boundary element method and the spherical vector wave function basis that is natural for the T matrix formulation. So in principle, like, there is no problem with this.
So probably, I mean, this implementation could really make fast. So the calculation when you have extremely small gaps. I mean, we are not thinking quantum effects now. We are thinking classical.
Like if you have really small gaps, and you have the really small gaps like localized. So you have, for example, clusters of particles that have inside the cluster they have small gaps. Mm-hmm. Then it's easy because you can calculate the T matrix for the whole cluster, and then you are working with those clusters.
Yeah, but when it's really small, the gap, I can see that you need a lot of terms. So became really slow, the calculation, because you need the convergence is really bad. Let's say another way. I mean, you need a lot of term or a lot of spherical harmonics, but really a lot. Just because it's not the best basis in that case.
I would maybe say no, because you need the like the spherical wave basis for the scattering, like between the clusters, but inside the cluster, you can have whatever basis you want. The only thing is that like if there are some effects, like for example some huge intensities in the gaps, as consequence of the external radiation. They would just have to like take this into account.
Yes.
But those small, like the huge intensities in the small gaps, will not have a considerable contribution on the scattered field.
But
in the location of the next cluster. So, yes, exactly. You can have this basis if you, for example, need to evaluate the intensities there. You can have this another basis. Evaluate the intensities in the another basis locally, but then like you have like the interactions between the clusters would be just in the spherical wave basis.
You think it will not affect the interaction of a cluster? So, I mean, even truncating, you think?
I mean, they wouldn't affect the interactions. You know, like for example, on a high multiple order in the outgoing scattering, if they have like some massive effect on the way how the particle or the cluster scatters, I think the massive effect would be visible in the lower multiples anyways.
Well, in the scatter between cluster, yes, probably yes, but it depends if you need the higher order in order to get. Yeah, I agree with you. I understand what you mean. Yes.
Because if you, this is something I also mentioned in the thesis, that if you need really to evaluate those like tiny details inside your cluster or your particle or your scatter in general, you can basically just use the same method that you use for evaluating the T matrix in the first place, which takes into account those details and so on, to like get back and evaluate, you know, all the intensities you have there and so on. But it's very unlikely, in my opinion, that then those small details would be visible in the spherical basis at some really high multiple degree.
Yeah, I agree. Okay.
Like there's a theory on this. It's like in general this is just a fast multiple method. It's a type of fast multiple method, and there's a theory about this, like how does it, you know, propagate, how the small details can propagate far away from the source. So yes.
Yeah, I agree with you. Well, I have to say that I'm definitely happy about all your thesis, your defense. You definitely deserve to get your PhD, and I think you passed very well this proof. And from my side, I don't think I have any more questions. You really answered well to everything, and so I have to say that you did a really great job. So from what is my concern, I think I'm happy with the job done, and I think it's I don't have any more questions. And definitely I can say that you passed very well the proof. Okay.
Okay, thank you very much. Esteemed audience, I ask those of you who have observation to make on the dissertation to kindly request floor from the custos.
I would like to thank Dr. Vincenzo Giannini for being the opponent.
It's a pleasure.
Yeah, I declare this defense closed.
Say again, sorry.
I declare this defense closed. Now, this was the
Yes.
statement.
Thank you.
Thank you. Yes, go home. Okay, so thank you again and bye-bye.